still looking at this.
So
We're still looking at this.
yeah, I figured, I'd just leave it up. Exciting. But yesterday, Dan's presentation with that, Nikhil's question about the strip of the vorticity back there, that's what I think has to do with driving the development of this conglomeration, right? It starts to get a little bit balled up, and then it turns into a major event. And then they had 4 feet of snow in Santa Rosa, California.
Is that when like turned back around?
Yeah. It was all in that deep drop. It was a really interesting setup. So. But I hadn't thought of that until yesterday, and maybe that's a worthy second level question. So.
We are up and running, so whenever you want to get started.
Okay, so welcome to our weather discussion. Don't forget, this will be the last one we have until the last week of January, because we don't do it during the break, and we won't do it next Friday because you got to be studying for exams, and I'll be damned if I'm blamed for your poor performance on an exam. Me or Patrick or Pete, we're not going to take that responsibility, so don't come here next Friday. Study instead. This is old, so we're not going to stay on this. So I want to show you some other new things instead. I just put this up there so you can be entertained as we go. So Pete, if we can go to this one right here. This is the current time series of the cold pool. I want to point something out on this. 8 of the last 9 days of the month of November were all-time record minimum aerial extents. And remember, on the 21st or the 22nd, I told you that through the 21st we were the warmest ever. Well, that 8 out of 9 last days of November guaranteed us. We just lived through the warmest Northern Hemisphere fall that has ever been recorded. That doesn't mean it's the warmest one ever, because we've only been recording it this way since 1948. UW-AOS has a reanalysis goes back to 1940 now. I haven't had my hands on it, but I'm going to do that. I suspect that the 1940s did not compete in terms of warmness with what we are at right now. So it's going to stand as at least the warmest one in the last 84 years. And that's pretty remarkable. We had only a few days, and they were at early part of the month, where we were above any of these 3 averages over the whole Northern Hemisphere. It's also interesting that those 9 days coincided with the coldest 9 days we've had in Madison. So that's just perfectly the way that it goes. There's no correlation at all hemispherically with what you feel at your own bus stop. And that's the way it is. But nonetheless, this is a really warm fall. There's never been a warmer one in the NCEP reanalysis record. And so I want to show you something else about this. We can leave this tab, Pete. If you take all of the now 77 years from 1948 till now, and you rank them with the number 1 on the list as warmest and number 77 as coldest for September, October, and then you do the same after December, January, and February, the subsequent December, January, and February comes along, you have 2 ranked lists. And it's interesting to see what a given season does from the beginning to the end of that season. So I call that a rank change. Let me show you what that looks like. That's right here. This is a whole collection of them from 1948 through, I didn't update it last year, so this is 2022, 23. So if you have a red spot in the year, that means that the year got warmer in December, January, and February. So you were lower on the warmest to coldest rank list for September, October, November, and then the winter came along and you went higher on that list. If you're blue, you went colder as the winter came. And as luck would have it, maybe you can even see it by eye, 37 of the years got colder as the winter came, 38 got warmer. So it's almost a perfectly even split between them. And I can't discern any other pattern out of this. I wrote some other interesting things down. There were 14 winters where it got warmer by as many as 20 places, so all of these few here. And there were 11 that got colder by 20 or more spaces on the list. The all-time, there were 5 30 or more warmer and 5 30 or more colder. And then the all-time biggest changes were in 2007, 2008, right here, and then 2011 and 12. And 2011 and 12 was the 6th warmest fall, but the 60th warmest winter. So we suddenly fell off a cliff that year and got much colder for the December, January, and February. So of course people have been asking me who I tell about the cold pool. They say, you know how I'm excited about records, so when we set a record, I want to tell everybody about it. So I've been telling people, they say, well, what does it mean for the winter? And I say, yeah, I have no idea what it means for the winter. So to me, this graph testifies to the remarkably short memory of the atmosphere. There's no way really to make any sense out of it, I don't think. Although it would be fun to look at a comparison of maybe the transition months, November, December, January, in the years that have the greatest change in a positive sense versus those that have the greatest change in the negative sense. Although I still don't think there'd be much to learn from that, unfortunately. But anyway, I wanted to show you this rank list change. There's nothing that can be said about the coming winter from this simple time series. Grant, do you have a question?
It seems like at the extremities of a list like that, you'd be kind of capped. Because if it's the warmest fall, there's no way for the winter to be warmer.
Yeah. That's right. You do have a limit on this. So you could use this as a guide for betting. And I say that not as a game, but I mean, think about it. Honestly, think about this. There are people who make a living at doing this, betting on energy futures, for instance. Is what we saw in the fall going to tell us anything about the wintertime? And you're right, there is a limit. You can't get warmer than we just were. However, a warm winter means something different than a warm fall. And so, but nonetheless, if you knew this was coming in the fall of 2011, you could have made a ton of money on buying energy in late November and selling it in February because it was cold around the hemisphere. But, I don't know how you can do that. But there's potential there for that. But you're right, the extremes are capped, and we're at the cap right now. We can't get to the warmest winter, probably. Wouldn't it be neat if we did that? If there was zero change in the rank list for this season, that'd be unbelievable. Okay, so that's it for the cold pool. What I wanted to do with my part of the discussion was talk a little bit about our weather system. So it's not going to be quite the same way we often do our discussion. I'm not going to show the current weather right now. I'll show it when we get to the current weather. But I want to start out with what happened this week. So we can get rid of this, Pete. I think we'll go to Alicia Bentley's maps. And I'm looking at just to remind you where we are, 0Z on the 3rd of December, which was Tuesday, is that right? Tuesday was the 3rd? Yeah.
Be Monday night.
So it'll be Monday night. And at the time, you're looking here at 850 temperatures in red and blue, and I think they go to blue when they go to 0 degrees, yeah. And then precipitation in the forecast, and then also sea level pressure. So you get a few things on this map all at once. And as you know, we had a really interesting Wednesday afternoon into Wednesday evening, Thursday morning. So I want to talk a little bit about what happened over that period of time. That will lead us to the current weather, which is still going to be related to what we had on Tuesday and Wednesday. And then maybe there could be a discussion about what was next after that. But so on Monday night, there's kind of a thermal ridge over the western part of Canada, and a strong baroclinic zone on the eastern side of that ridge. And here's Lake Winnipeg, and Great Slave Lake is right up there in the Northwest Territories. And so you can see this chain of lakes in Canada, and that is immediately to the east of the Rocky Mountain chain. So there's this, maybe it's kind of a lee side trough in this region of Alberta, Alberta, British Columbia, but there's this very weak region of sea level pressure minimum there, 1,008 millibars. If we can go to the variable, we'll bounce between these two variables. We'll go to the 500 millibar vorticity, which is right there. And at this time, there's no discernible shortwave embedded within this long wave trough. So that's the whole complexion of the flow. And that leads me to believe that there's a lee side warming going on right here, because that's about where the mountain chain is. And there's flow straight across it. Just up here on the northern edge of the archipelago, you can see a little bit of a trough axis. And we're going to see what happens to that in the next couple of times. So let's go back to the sea level pressure and 850 temperature. That's at the bottom here. And then let's click forward a couple of times. Let's just use the arrows to do that. And you can see the cyclone emerges out over the Canadian plains, and it starts to deform that baroclinic zone. Not only deform it, but incorporate it into its broad structure. And so you can see that going on. And this is now 12Z on Tuesday. Let's see what the 500 millibar vorticity looks like. Thank you, Pete. And at the same time, one sees kind of a broad northwesterly, west-northwesterly flow. Here's the region where that cyclone is beginning to develop. There isn't really an obvious or very potent upper shortwave, but notice this troughiness over the archipelago is kind of making its way, rotating around counterclockwise, and this finger of larger vorticity is on its way to a rendezvous with this disturbance. But at this time, it has no impact on it. It's too far away to have much impact. So that's still a lee side feature trying to emerge from the high terrain. Let's go back to the sea level pressure 850 map and click forward a couple more times. and maybe one more. So we're kind of stuck over Lake Winnipeg. The baroclinic zone starts to look a little bit more organized on the back side of this, with strong northerly flow near the ground. And this is when we had sort of maybe our warmest part of the week, a little bit of warm air advection at 8:50. It wasn't too bad on Tuesday afternoon. So here's 0Z on Tuesday evening. So let's take a look now at the 500 millibar map, and I'll put, again, the pointer right where the sea level pressure minimum is. It's not really tied up with a very strong upper wave right at this moment. However, the feature that's been kind of rotating cyclonically across the coast of the archipelago is now kind of moved into central Canada, and it's not that far away. Here's Lake Winnipeg, where the cyclone was. It's not that far away from the surface disturbance. And so now there may begin to be some kind of mutual interaction between these two things, and of course that would spur a subsequent and more intense development of that cyclone that's, you know, been struggling to get out of the high terrain and shed its lee side characteristics. The other thing that's really interesting about this shortwave feature is that notice how the isotherms at 850 are aligned in such a way as to suggest that there's some cold air advection in the presence of perhaps some cyclonic shear. This is too low to really matter for upper fronts, but if we go back to 500 millibar, we are at 500 millibar, sorry. I was confused. This is exactly what I meant to say. Strong cold advection in cyclonic shear. The wind speeds from the northwest are much more intense here than they are further to the north and east, and there's cold advection. That means that this vorticity strip is probably come down from the stratosphere and is certainly being continued to be forced down from the stratosphere. The synoptic environment is perfectly aligned to intensify that tendency. So let's go ahead, go back to the surface map again. Remember, now we're going to get to about midday Tuesday if we click ahead 2 times. And that's when we're starting to wonder, hey, when is it going to start to snow here? The thermal ridge part of this structure is just over us at 12Z on Tuesday. Everybody was waiting for this really intense, look at the pressure gradient force over Lake Winnipeg, and the intense cold advection. And localized cold advection leads to strong subsidence. There's a lot of stuff going on here. It's windy, cold, snow squalls, which actually emerged in spite of the discouraging environment that were there and probably enhanced by the lakes. Meanwhile, pretty intense anticyclogenesis going on the sort of central part of the Canadian chain of lakes, right in this location. This is 1024, 8, 6, sorry, it's Alicia, so 8, 32, 36, 10, 40 millibars, and here we're down to 1,000, just north of Lake Superior. So we got a 40 millibar gradient over a pretty short distance, a 40 millibar difference over a short distance. Let's see what the 500 millibar map looked like Tuesday morning. Oh boy, that's pretty interesting. Okay, so that looks like a sort of a amalgamated upper vorticity maxima. Notice very obvious and strong region of cold air advection and cyclonic shear. This thing's going to get more intense, is what it would tell me. It's on the upstream side of a trough axis. It's getting more and more isotropic in its shape as a vortex structure. There's ample baroclinicity, so the thermal wind is strong, and one can imagine pretty decent PVA by the thermal wind right over the Lake of the Woods. In fact, let's go here and just remember the vorticity max is right over Lake Winnipeg. Go back to that other map, Pete, because 850 isotherms will give us a pretty good proxy as well. And so, yeah, you can see pretty strong PVA by the thermal wind up in this region. And that means that the northwestern portion of this cyclone starts to develop sort of an inverted trough structure. And you'll see what happens to the cyclone as it continues to move to the east. The pressure gradient flattens out near the middle because things are getting reorganized in different spots in reaction to the presence of this upper wave. So at this time, 12Z on the 4th of December, can we switch back to tropical tidbits? We'll take a cross-section through this thing. And I think I have it right here. So we'll have to click forward to that time, which will be several clicks. 12Z on the 4th. Yeah, perfect. And so let's go sort of right through like that line, sort of like that. And then let's take a look at the PV. Just gonna find it. Yeah, so here's the, let's see, this is the north side, so it's up here, and this is the other side down here. So a pretty intense jet coming out of the page at us, and here's a sort of a very intense tropopause undulation of potential vorticity. So there's a strong upper trough that's developing here. It doesn't really look quite like an upper front at this time, because it's not quite all put together, but things are starting to happen there. So pretty intense, 120 knot jet right in that location coming out of the page. Okay, let's go back to Alicia's maps. This is different kind of driving. Pete can do any kind of driving. Give him a tricycle, I think he could drive around. Let's go a couple more times. Notice, look at how the pressure gradient force is getting weak in the middle of this disturbance. That struck me as odd. It's not really, the pressure is not falling in the middle anymore. It's kind of getting itself reorganized. You'll see what I mean later. This is about the time the front was coming through for us, late in the afternoon on Wednesday. Very intense cold advection. We had snow squalls and the winds were snow devils all over the place at 9 o'clock. The timing was a little wrong. If it had been 6 or 12 hours later, we would have had exactly those conditions over a relatively warm Lake Mendota, and we would have had steam devils on the lake. So it didn't quite work out. I was hoping the next morning it would be like that, but it didn't. Things had become a little more quiescent by then. But you can see not much development of the cyclone. In fact, a weakening of the sea level pressure gradient near the center of it, which is odd. And then we're still in the 1040 range here, just about to come into the Dakotas. So let's take a look at the 500 millibar map at this time. The cyclone center is right here. And I think you start to see maybe why things are getting a little bit strangely organized. The maximum of vorticity is right over the Mississippi River on Wisconsin-Minnesota border. That's an intense upper front right there. And probably the head of it, indicated by Alicia Bentley, puts vertical motions here that are not quasi-dystrophic, they're from the model. But the head of the vertical motion is well south of the position of the surface cyclone. So this is not any longer the place that's favored for development. Development's going to be maybe re-establishing itself somewhere south of that particular center of the cyclone. Let's take a cross-section through there on the tropical tidbits if we could, Pete. And we'll click ahead to the same time, which was one more time. Yeah, so I think we were kind of right there along the Mississippi. It'll be pretty good. And that's a guess. I'm going against my instincts to cut right through the thickness field, but let's see what it looks like. Yeah, it's a bad angle, but we'll go for another one in a second. But you can see an intense jet, and this is just a bad angle. But notice the baroclinicity, the green lines are theta lines. That's a strong frontal boundary that actually has a couple of feet in the ground, but mostly it's in the mid-troposphere. Let's go back here and draw it right through the thickness field, perpendicular to it. So we'll go right like this instead. Yeah, it probably will look a little better. Now, it looks about the same. The baroclinicity is a little more intense. So that's a deep, intense baroclinic zone. Not super sharp, and the lack of sharpness, I think, also gives us a sense that we haven't yet put this PV pendant together in the way that may be the case later on. I think, in fact, it is later on. So, but notice the bifurcation of the baroclinic gradient in the lower stratosphere is quite intense, and then here's one in the upper troposphere, and then there's a region where there's almost no horizontal temperature contrast. And that's about where the jet core is. Really nice picture. A little bit weird in its geometry. Okay, so that's what came through us on Wednesday night. We'll go back to Alicia, because it's a better close-up, and we'll go back to the surface now. Then let's watch subsequently what happens to this disturbance. So let's click ahead a couple of times. Seems to me like it's starting to find its feet a little bit further south of where it originally was. Here's the strong thermal wind region. So this is where the 850 temperature gradient is really intense. And if we look at the 500 millibar vorticity, again, I'll put my pointer at the cyclone center. Is this the same time? I guess it is, yeah. And you can still see that really the strong vertical motion forcing is out here. It's not right there. And so the cyclone is still not at the minimum in sea level pressure is still displaced from the maximum location of development. And I think we'll see that if we click ahead a couple more times.
You can go back to the surface.
Yes, thank you. I didn't have to say it, we knew that. Right here, see what, going back one, right here where you start to see this intense precipitation in the forecast with still a not so well organized sea level pressure minimum. We're still at 1,000 or 992 millibars in this region. It's been 992 for a while over a wide area. It's not really focused, beginning to get focused in the precipitation shield, partly because you have a really intense localized region of warm air advection right in there, and that produces strong ascent. I'll show you why in just a second. Let's see what it looks like at 500 millibars. I want to see that point right there where the heavy precip is. Yeah, that's where all the vertical motion is. That's down shear of the big vorticity strip. This is where development's going to be going on. Right here in the Gulf of the St. Lawrence, river between Newfoundland and maritime Canada. So that's where everything's going on, and the cyclone's going to re-establish itself. We go back to the surface analysis, or data, and then we'll click ahead a couple of times. Now we start to see a concentration of minimum sea level pressure. One more time would be great. Look at how intense the pressure gradient suddenly gets. That's because you really got a focused region of ascent right here. This is where the pressure's falling most rapidly, and everything starts to congeal around it. And so you get a really intense disturbance. These are isotherms again, remember. Very intense warm air advection. And we don't have a blackboard that's easily accessible. I'll do it over here. I have to show you this because it's so cool. Concentrated horizontal temperature advection. Here's some isotropes in the XY direction. Here's a really strong eutrophic wind there, a weak one here, and a weak one here. So that gives you a concentrated warm advection, right? There's two ways to think about this. This region right in here is going to have rotation that goes like that. That's anticyclonic, that's cyclonic shear. This one's going to induce rotation like that. So that's negative what this means, this is positive what this means. There's your thermal wind, parallel to your isotherms, very intense PVA right there. That's one way to think about it, right? Another way is, if you think about the Q vector, at this point and at this point along the isotrope, you have to add this wind to this geostroke wind to get that one. You've got to subtract that one to get that one. And if you take the vertical cross products of both of them and flip them, there's your Q vector on that side, and there's your Q vector on this side. So there's really strong Q convergence there too. And it's along the isotrope, which is a species of PVA by the thermal wind type. So anytime you see a concentrated region of strong temperature advection, you can bet there'll be huge vertical motions there. Let's go to right there.
Sorry, I'm multitasking here.
Sorry?
I said, sorry, I'm multitasking here.
That's not like you, Pete.
Once in a
Actually,
while.
Pete's the chief multitasker on the planet Earth, as far as I can tell.
All right, where are we going?
Let's go to my vertical motion plot. And 6 hours into the forecast, I think would be now. Look at that intense vertical motion there. That's exactly where that strong warm air advection is. It's really focused. That's a concentrated column of air that's rising rapidly. And that stretches the column and spins up a vortex underneath it. And you can see suddenly this cyclone takes shape. And while we're here, let's go back and split this up. This is the total omega. Here's the part that has to do just with the long isotrope Q vector. And that's really the concentrated thing we were just talking about right there. No appendage. Now let's go to the transverse part of the Q vector, which attempts to show us something about the frontogenesis. It does a pretty good job. These dotted lines are thickness lines. Here's the ascent in the warm side of the cold front, descent on the cold side. Really intense ascent in the warm frontal region because it's a little more frontogenetic. And you can see hints of an organized descent on the cold side of that. So this is contributing a little to the cyclogenesis as well, but it's mostly the long isotrope Q that's driving the intense cyclogenesis. So that gets us down to the satellite picture. So this is how it starts to look more like a normal weather watch. So let's take a look at the current East Coast satellite image if we could. And look at this thing. So we were talking right there at the Gulf of the mouth of the Labrador Sea at the current time. That is going wild. Can we do the infrared so we can see that cloud head? Yeah, great, thanks, Pete. That's a massive cloud head that's developed here. I left off by showing the vertical motion being forced here on the Alicia Bentley maps, but now we've moved out. It's the same structure that's doing it, and you can see it in the QG omega. This is really an intense development area. Now, to the extent that the 500 millibar wave, which we'll look at in just a minute, stays sharply curved, this thing could keep on getting more intense. It looks like it's going to flatten out a little bit, and the storm may turn into, may go into a decay phase along the east coast of Greenland. But I wanted to point out how it started out as a really innocuous little disturbance, probably forced by lee subsidence in the lee of the Canadian Rockies, slugged along through the plains, waiting for something to pinwheel out of the archipelago, that thing that pinwheeled out was perfectly primed to produce an extraordinary stratospheric subduction, put it in the right spot to really bring this thing to a development phase. It took a while for that storm to lose its lee-side characteristics, and in this instance, I think that losing of those characteristics was the sea level pressure minimum was displaced from the region of strongest developmental potential for a while. And so you had a flat pressure gradient in the middle of the thing, and then suddenly, when everything was aligned the right way over the St. Lawrence River Valley, it went wild. We're about to go into the field, not this winter, the next winter, I think. Andrea's not here. And try and investigate high Arctic disturbances called tropopause polar vortices. And I think this could well be a case where a tropopause polar vortex, and they're diabatically driven by cooling of stratus clouds, maintained and driven. And that thing from the archipelago came in and got this monster storm going. There will be instances where this storm is only beginning to intensify, and then will find its way into the North Atlantic and utterly alter the North Atlantic flow and the flow downstream over Europe. This one, I think, won't quite do that, but it would have been a great test case to examine, a 2 or 3 day evolution with highly detailed in situ observations of the interaction of a tropopause polar vortex, a lee-side trough, and an Alberta clipper, which populates our winter like crazy here, and then turns into a major Atlantic storm. And that's one of the goals of this project. So I think if we could see something like this when we're in the field, it'll be fantastic. Okay. So let's take a look at a couple of the upper level chart speed, and then we'll be done with my part. And I'll actually give Patrick some time today. He knows I stole it last week. So here's the 12Z map this morning. And so here's our disturbance, and now north of the Gulf of the St. Lawrence River. So here's Greenland. And so we've got the strong curvature maxima right over Newfoundland. And there's not the strongest downstream ridge. And that probably is being changed as we speak, because that cloud head has got a lot of latent heat release that's certainly encouraging ridge building there. And you're moving out over still cold but relatively warm water, and so there's going to be a nice potential for development there. Not only that, but for the oceanic circulation, Liz isn't here. I always argue with her about this, but she, of course, knows thousands times more than I do. But if you rake the southern part of the Labrador Sea with winds in the 40 and 50 knot range, you can't help but cool the water down, it would seem to me, and evaporate water and make it more dense as a consequence. That forces the sinking of the North Atlantic conveyor. And if you suddenly had a change in your storm track or something like that, that would be related to other changes in the climate, that would be a problem, because you'd change some of the pumping there, I would think. So this is a classic candidate for thank you for your contribution to the Atlantic meridional overturning circulation. This is certainly going on there. Northerly flow, northwesterly flow from the archipelago all the way down to Dayton, Ohio. No particular thermal advection at this time along this northwesterly flow, so probably no development. But that can change ever so slightly if you have stronger and stronger subsidence as you get close to the base of the trough. It's greater sinking here than up this way, so these isotropes will get turned a little bit that way. Because you're warming them up down here and you're not doing anything to them here, and then you can orient the isotropes into a configuration where there's cold advection along the shear, and then you start to get development. I don't see that happening over the next couple of days for us. And then a big ridge kind of over the Canadian Rockies and also over the US Rockies to a large extent. Let's go to 850 millibars, where we'll have a nice surprise that we'll all enjoy over the weekend. And that is, here's the rough position of the baroclinic zone over North America. And there's a little bit of a wave just over the southern portion of that. It's enough of a wave to induce, we're already seeing it, warm air advection. It's -5 at Minneapolis, it's -11 at Green Bay. So the warming is coming, and it's probably going to be fairly prolonged. I'd say the whole weekend we're going to stay either in the warm advection or then maybe reside in a region where we're already warmed up without the threat of subsequent cold advection. Either one gives you a pretty nice weekend compared to what we've had over the last week, temperature-wise. So that'll be nice. Look at this beast over maritime Canada. That's the one we just saw on the satellite. Look at how concentrated that warm air advection is. It's exactly what forces the vertical motion in this location that we just saw. So it's a really beautiful example of rapid intensification over a broad area. This is not a small-scale disturbance like the one we saw a couple of weekends ago off the coast of the West Coast. This is a broad-scale development and really a fairly intense one on the Labrador coast right now. Okay, so that's what we have broadly for the current weather. And this thing looks a lot more impressive than it did when it came through us. But if you lived here and you were looking at a weather map and you didn't live here, you'd say, that's not such a big deal. If you lived here, you know it was a big deal. So it was kind of a nice juxtaposition of not looking so impressive, but being impressive, and now also looking impressive. So that's what I have. See you in January. Have a good holiday. Okay.
Perfect, thank you. Can we start with the infrared? I think it was up still, maybe.
This is the old, is this the new one?
That's the West Coast.
And I'll start with North America, please. Because a valid question would be, we're gonna have a warm-up, is it gonna stay warm? And what I'll tell you in the short answer is no, because if you see, you can make out already in Canada, even in areas of Ontario, this blue and green that sort of retreats and the green up here that's not moving, that's because there's snow cover that is as cold as the clouds that are moving above it. This snow cover has developed pretty rapidly. 2 weeks ago, we didn't have any, most of Canada was snow-free. Now we have snow cover all the way to the Canada-US border. So now it's easier for these systems to stay cold and remain cold as they come towards us. And so keep in mind that we have snow cover here. If we could go to our climate page, please. And I'll just highlight how cold it was. Use that as a stepping stone. So if you look here, here was our little cold snap we had the past couple of weeks. You see, there were days where the high and low were below the average minimum temperature. So this is how cold it was anomalously. And we've stayed relatively below this mean line for a while. It looks like we're gonna have a warm snap and then we're gonna keep going down. But if you thought it was cold, it is anomalously cold even for Madison at this time of year. We're still largely above freezing, and we've had days where we've been in the 20s and close to 20 degrees. We haven't even barely made it above 20. So very cold, it's gonna warm up, and then get cold again. Let's look at why it's gonna get cold again.
I'm looking at that red line, and right around now, there's a pretty significant drop. Those are actually the 30-year average by day. It's not smooth. What do you suppose is going on there?
It's a good point.
Like the lakes freeze or something, or?
Could be lakes freeze. I wonder if this is when Canada freezes over usually.
Yes, that's a pretty significant
Yeah,
shift.
That's right. We're
Yeah.
talking about this drop off that
That is
is
interesting,
consistent. And it also, you can see it in the minimums too.
Yeah, right.
I didn't notice that.
I can see the January thought too, about January 15th-ish,
That's right, yeah.
even farther over, yeah.
Yeah.
I'm thinking like this.
Yeah.
Oh, that one, yep.
And minimums too. Minimum.
That's interesting,
I
yeah.
don't know.
So maybe it is climatologically normal that we cool down, but the rate at which we cool down is definitely much colder than normal.
Right.
So if we could go to our AOS forecast page, please. It's a good thing we brought up the tropoplasmic polar vortices because there's going to be one that affects us. Let's go to 500 millibars at 24 hours. And so you'll see this is the 500 millibar map. We usually look at synoptic scale waves. The system that's going to hit us is this little vortex. This is basically in the Arctic Circle near the North Pole. These things are subsynoptic scale vortices. You see it's an area of relatively high positive vorticity, or relative vorticity, excuse me, and it's smaller than these synoptic scale waves and systems like this trough over the west coast. This is the only thing associated with this tropoplasmic polar vortex, but we'll watch its evolution because this is going to impact us going forward and produce our cool down here. But you'll see, so this is a 24-hour forecast. This thing is still well up in Canada, so it's not really relevant at this time for us. Here's the hint of our warm-up. We're now into ridgy conditions, so you'd expect downstream of a ridge, we have clear skies, potential warming for our region, and that's what's going to be the case. We could look at the surface map at the same time. You see, here's our system. You can barely even make out anything associated with it, but here's where it's located. You'll see here's our nice warm-up where there's a broad cyclone up in Canada. Around it is counterclockwise flow, so we are in westerly flow and we get warm-up as associated with this. The warmer thicknesses to our west are, and the wind is advecting those warmer thicknesses to our region. So by tomorrow morning, we'll be in nice warm advection should be a nice weekend, maybe 40s and 50s for us. So if you can get outside, I would recommend it. And you'll see it's not precipitating as well, so it should be sunny, or at least not raining. Which we've had some weekends where it's been rainy and cloudy and cold, so definitely tomorrow and into Sunday we can get out and enjoy the weather. Could we go to 48 hours, please, at 500? So remember, our thing was situated up over, well into the Arctic Circle. Now it's sort of making its way down south into mainland Canada at this time. You'll see it kind of gets congealed into a larger system, but it's still not as big as these synoptic scale troughs that are moving, over our region. We're still in westerly flow, so you can imagine we're still under ridge condition. Continued warming into Sunday. Let's see if that's the case from the surface map, please. And you'll see that is the case. The thicknesses have warmed up. Now we're in relatively weak winds, so even Sunday morning, it'll be warm and not windy, so if it's sunny outside, I'm sure it'll feel great, especially what we've had. Here's the evidence of the tropopause polar vortex. You can see really cold thicknesses as indicated by, here's this solid coal or solid yellow line, and you can imagine the winds are advecting these colder thicknesses down into Canada. So this is the feature of interest for our region. Not necessarily the low pressure system associated with it, but these colder thicknesses here. Can we go 72 hours now at 500? And we'll see, this is the main feature associated with that polar vortex. And you'll see it's made its way pretty far from the Arctic Circle all the way down now into getting into central Canada. And we'll watch it continue to rotate around this trough feature, but it's this vortex strip that's the tropopause polar vortex. That will affect us, and you can see flow is now straight from the Arctic Circle all the way down into central Canada almost at this time. And remember, there's snow cover. So this thing isn't necessarily warming as it's moving south. These things are inherently cold and they remain cold as they move, but you have snow cover. There's not a lot of light coming into the Arctic at this time of year, so there's no real encouragement for this thing to become warmer. It's just going to remain as cold as it was in the Arctic, and that's going to be the case here. And we'll see that in the thicknesses, but this is the main feature. Just to the west of Hudson Bay, can we look at the surface at this time? And this is Monday morning. You'll see here it is. There's a nice ball of really low thicknesses. This is down below 500 decameters, how cold this is. And you can see the associated advection. This is straight cold advection. And this flow is uninterrupted all the way down from northern Canada into the Central Plains. Not exactly the coldest air yet getting into the Central Plains, but we'll see this thing continue to move south. Places that are snow covered in Canada can get well below -20, -30 when these things move down. And it's already early December, and we have one of these really cold shots of air coming down here. So if we could go 96 hours now at 500 millibars. Here's the feature of interest. So now it's moved pretty much all the way halfway down this entire map projection. Now it's making its way down into southern Canada, just north of the United States. There's the trough that's sort of rotating around, but it's this southern appendage is that tropopause polar vortex. Let's see the thicknesses at this time. So it's right around central, or south central Canada, right there. And you'll see here's this shot. Really cold air. It looks like the shot of cold air we just had, where there's this bulge of really cold thicknesses and really strong advection right in the middle of it. So this is that localized, kind of the opposite of what Professor Martin was showing.
Yeah, that's right.
This is local maximum of cold air advection, or a local minimum of temperature advection. And this is uninterrupted flow all the way down straight into the United States. And you'll see these lower thicknesses. They even got colder as they move south. Now it's 490 is the lowest thickness associated with this tropopause polar vortex. If we could do one more time, we'll go 24 hours further to hour 120. Now we have this, I haven't even discussed what this is, but this tropopause polar vortex, which has moved down, it's sort of rearranged the entire flow over the United States. Now we have straight northerly flow all the way down into our region, but definitely into the northern part of the United States, where that vortex is more closer in proximity to. It is now beginning to rotate around this trough feature. It's going to produce a pretty significant system, but I'm not going to talk about that. I'm just going to talk about how cold it might get for our region. If we go to the surface now, we'll see the bullseye of really cold thicknesses now is just north of Minnesota, and it's 489 is the minimum height within that. So it's getting colder as it's moving to the south, and these are extremely cold thicknesses. This is the 510 decameter line, the rain snow line, if you can call it that. The 540 line is all the way down to the Gulf Coast. And so this is our potential for really cold air, another shot of really cold air. Tropoplasmolar vortices by nature are dry. They come from the Arctic. There's really no moisture in the Arctic, so not a lot of associated precipitation with it. What is going to produce precipitation is the development of cyclone out ahead of it. But for our region, this thing develops well to our east, so it's not going to affect us. What's going to affect us, these really cold thicknesses here. If we can pull up the 850 loop, please.
Yeah, I was looking at that earlier.
Yeah, we'll see this. If we could stop it. We'll start from the beginning here. And click forward to like 24 hours, please. And then we'll let it play. So you'll see here's this appendage of cold air associated with the tropoplasmolar vortex. We've just clicked forward a couple times. And I guess if you just keep wanting to click forward, you'll watch this. Here's this shot of cold air. It remains cold, remains right around minus 30. And look at it make its way all the way down into the United States here. For context, the only colder place is Greenland.
And it's 3 kilometers above sea level.
Exactly.
On
And this
ice.
is a 4-mile ice sheet. Here's air at the surface, close to the surface. So this is extreme cold air. How cold it's going to get, that's still unclear. It looks like it'll get colder, obviously. Not quite sure if we'll get below 0 from the shot of cold air, but there's a chance with this cold air making its way down. And you can see it connected to the Arctic by the temperatures here. So if you want to just click forward a couple times
I don't know
to,
if Milwaukee's bought into this yet, because I was looking at their local forecast from this morning, and they only had as low like 11.
that's right. I don't know at this point. They might be concerned with where is this going to actually set up.
Yeah.
Because if this changes orientation, either a little north, a little south, that changes the whole nature of the game. You can see it doesn't make its way quite into the United States, but it moves along the border and then goes back into the Arctic essentially. So that's the next shot of really cold air for our region, and that's Tuesday and Wednesday. This coming week, so you can see that.
And in support of that, Patrick, I should have mentioned, there was a minus 48 on the 12Z 500 millibar map in the northern archipelago.
Oh, that's right.
And
Yeah.
that's as cold as it ever gets at 500 millibar.
Right.
So you're right, this is really,
Yeah.
Lance calls it creme de la creme of cold air.
That's right. And you'll see it almost. Let me see if that's the case. I'm watching what happens with Greenland.
Probably warm advection from the series of cyclones
Yeah,
that
that's
blows
right.
that air right off there. It was also
So it's not-
artificial in a way.
Yeah, that's true, because it's Greenland, but yeah, so very interesting shot of cold air.
Yeah.
So we'll watch this, see if it actually develops anything. And it develops a pretty intense cyclone. Right where that cyclone is affecting right now, you can see that in 850 temps. And the heights, I guess, as well. So this will be an interesting thing to watch.
Yeah, I'm intrigued by, what the relationship between an active Pacific storm track and such a cold air outbreak over the central U.S. is, in the sense that
Yeah.
maybe the ridge building over the west coast is a really important part of funneling that air straight southward.
That's right,
If it
yeah.
weren't ridgy there, it might be easier to just kind of move in whatever direction it wants, but it's kind of
Yeah.
compelled to move straight southward for a while.
Exactly right. You can see that if we wait to the beginning of this. You can see there's relative ridginess, and it rides along that
Yeah.
ridge, yeah.
And a cascade of really intense storms that kind of crashing
Yeah.
into the Aleutian chain to build that ridge.
That's right. So it is short-lived, relatively. We'll see it makes its way, and then we warm up again. But it is another shot of cold air coming. And that's all I have. Does anybody else want to see something? Yeah.
I was just wondering, so I assume there's multiple of these at one time? It's not like in the stratosphere you just have like one big polar vortex?
Yeah. These are not the polar vortex, as it's called. These are locally subsynoptic systems that move from the Arctic. That tropopause polar vortex is just the large-scale circulation around the Arctic. You have local radial cooling, and these can move down. They do move down all the time. There's a lot of them, but when they happen in winter is when you get noticeable impacts because they're cold features. So you move cold air anomalously south, where it's not necessarily cold yet, especially since it's December, and that's when you begin to notice the impacts, yeah.
Yeah, and the nature of the interaction between these really small scale, you described them nicely, they're really small scale vortices that are both developed and supported by diabatic cooling off of stratus clouds in the Arctic.
Yeah.
And there's no sunlight, so you don't have any compensating warming, so you're cooling them forever, and you're creating PV in the tropopause level by that cooling.
Yeah.
So you start to produce these little icicles, these stalactites of PV at high latitude. And to the extent that the mid-latitude flow is wavy, like it is right now, when it's active, they can be ingested into the middle latitude flow and really be potent cyclogenetic agents.
Right.
And that's what we're hoping that we'll learn more about, is how do they connect? And do they connect to upper frontal developments, which are probably even more pervasive at the boundary between the high Arctic and the mid-latitudes? And how they get themselves involved and interact with those developing structures is a great mystery, but it has a lot of importance.
Absolutely, yeah. Could we pull up the loop of the tropopause? And I'll do the pressure. These are very easy to see from this loop. You'll see. Yeah. So watch, here's this. The warmer colors mean the tropopause is closer to the ground. So you'll see
Right there.
right there, you can see it. I guess there's a couple of them, but each one of these locally depressed tropopauses that come from the Arctic are one of these tropopause polar vortices. Yeah. So they're always being injected into the flow.
And the other thing about them is that they're long-lived because they have this diabatic component that grows them and keeps them sustained. So it's like a little diabatic greenhouse for these things in the high Arctic when the sun's down. So they last a long time, and they can migrate around the hemisphere and find a connection.
Mm-hmm. And they do.
Yeah, occasionally they do, yeah.
They're called the same thing as the tropopause polar vortex, so it's kind of confusing.
Oh, yeah, I didn't realize it was just a
Yeah.
different feature.
Yeah. Anything else?
All right.
All right, well, good luck on finals, and we'll see you in January.
Thanks, Patrick. Thanks, Pete. Luck is a species of talent. Apply your talents.